So thank you for the kind introduction, Ian, and also to Dave Bamford for organising the event today and inviting us to participate. So I was going to call to name this talk "How to Hunt Elephants Successfully with a Pea Shooter," and the reason for that was that when I was running VibTech with my co-founder Bill Park, who's in the audience over there, we were looking for money, and one of our potential investors sent our business plan off to some old trustee somewhere in Texas, who came back saying, "These guys, they're just trying to hunt elephants with a pea shooter." Well, the fact is that we looked at things differently. The radio that we used, we turned what this guy saw as the weakness of the system into the system's major strength. So with all these radio applications, it's a matter of thinking differently to other people. So Bill and I did the same in VibTech, which gave rise to the Unite system. And Wireless Seismic has done the same thing with the way that they manage their radio networks with the RT system too. So as it says here, it's the industry's only scalable real-time cable-free seismic acquisition system. And that should have moved forwards. There we are. So the company, and I know that a number of you are probably here last year, so I'll just run over the background to the company quite quickly, and I'll be in the networking event afterwards, so happy to chat to people if they want more detail. But the company was founded in 2004, and we incorporated in 2006. We have funding from Chesapeake Energy, from Energy Ventures, which is a Norwegian venture capital firm, and last year from Total Energy Ventures. We have our headquarters in Houston, in Sugar Land, and we also have, for historical reasons, an engineering office in Boulder in Colorado. We've got 80 full-time staff. We've got 9 patents granted. We've got about 15 pending. And we launched our first commercial system in 2011. And that system, for some ludicrous reason, was called the RT System 1000, which led everybody to think that the system was only capable of handling 1,000 channels. So around about that time, we had a change in management, and we actually withdrew the system temporarily from the market. And we made some very significant changes to how the system worked. And we launched that at the AGE in 2012, and that was the RT System 2. And since that date, we've got 15 commercial systems out in the field. So this is our 4th year of presenting at the Finding Petroleum seminar. Each year, we've made significant progress. We've made a lot of promises as to what we're going to do with the system. And indeed, we've really met those milestones that we put down for ourselves. But I'd like in this talk really just to highlight 2 key areas. One is the success that we've had in scaling the system up to large channel counts, and the other in ruggedizing the radio network to make it really very much an automatic thing and automatically self-healing. So, there are lots of skeptics out there about using the radio-based systems. We've all heard of the technical drawbacks of radio systems, but a lot of them are myths or perhaps wishful thinking, people wanting the system not to work. And a lot of these things have been overcome by wireless seismic. So we're gaining really very significant momentum in the market, and there's still a lot more to be done. And I think the great thing about where we've got to now is that we know what the course ahead of us is. So the system really it's best conceived as a cable system where the cables that are used for data transmission have been replaced by a real-time radio telemetry system. So we can do continuous recording that you might want to do in frac monitoring, or we can do, indeed in the vibro-size techniques, or we can do a data on demand type of acquisition technique that you might want to do with dynamite or an impulsive source. The units that we have here, they're ultra low power consumption, and we've put a lot of work into reducing the power budget of the units. Because of the low weight of the system, we can claim that we do give significant HSE advantages as well as a reduced footprint of our operations just through needing less people on the crew. Our radio networks, as I said a little bit earlier on, really are self-sustaining, and there's very little need for any user intervention in making the thing work. We've now collected data in a great number of commercial projects. Obviously, as an American company, a lot of these are in Texas, Oklahoma, and so forth. We've also expanded our operations overseas into the likes of Poland, Colombia, Bolivia, the jungles of Indonesia, Kurdistan, and China. And the system is now scalable to tens of thousands of channels. So what are the industry challenges that are addressed by our system? I think we're all aware of the challenges that we have with cable systems. They're difficult to maintain, they're costly to repair, they need a lot of people on the ground, they're difficult to transport, there are sometimes difficulty in deployment, and they're very labor intensive. There's also a significant HSE exposure. This poor guy here is having to neck roll this pretty significant cable. That's not a nice job to have to do. Cables, for some reason, animals seem to just love them. We don't know why. Maybe it's something that comes off people's fingers onto the cables, but okay, that's a pile of geophones. That would affect RT system too as well. But it really illustrates the fact that animals are a big hazard for cable systems. So one of the responses to trying to get away from the shortcomings of cables is to use autonomous nodes. And autonomous nodes give a fantastic level of production and productivity for the seismic contractors. They're quick to deploy. You don't need to communicate with them back to the control center. And if you're worried about coverage or redundancy, you can over-deploy the systems in the field to overcome any potential problems with data loss or theft of units. However, one of the challenges that we have is that you can't see the data while you're recording. You've got very limited quality control during acquisition. And you might think, oh, well, that's, I can live with that. But I was in Australia just before Christmas visiting one of the major coal seam gas companies there. And they'd been doing some work with a nodal system. And it took them 2 weeks to get their test vibrator sweeps back. And then it took them a month to get their data back. And at that point, they discovered that the nodes hadn't been deployed properly. They weren't coupled to the ground in many cases, so they had real problems with the data quality. Another issue, and this is the Unite system that Bill Park and I developed, that is really used mainly in an autonomous mode fashion these days. So you have to go out and harvest the data. So typically that's done manually. It may be heavily automated, but you've got to send people onto the line to do that. And another issue is the fact that you have to have quite complex data transcription to put the data back into some kind of trace sequential order. So the upshot of that is that you have to have some quite highly qualified people on the crew that you otherwise wouldn't have to have. So you can see this guy here, apart from the fact it's too small to do his job, he's got 2 step ladders there to be able to reach the shelves that he needs to get to. That is not a field labor person, that's a highly paid person. The other thing that the nodal systems don't tell you about as well is that you need between 10 and 15, sometimes up to 20% of extra capital expenditure just to cycle the units through the data harvesting center. So that's a hidden capital cost for the units. And of course these systems, they need very large trailers and base camp infrastructure to house all the battery charging infrastructure and data transcription facilities. So in conclusion, autonomous nodes, they do overcome a lot of the limitations of cabled systems, but they introduce in their own right some other limitations that aren't there for cable systems. So with the RT system 2, we get around a lot of the nodal issues. We still have the extremely high productivity that the nodal systems offer, but we don't have some of the drawbacks. And with our system, all of the data is delivered back to the central unit in real time through our high capacity radio network. We have a real-time noise monitor, so you can see what's happening on the spread at all times, and we have a continuous feed of QC data back to the central. The system itself is really very straightforward. It comprises 4 main items. The first is this wireless remote unit. It has what's essentially analogous in a cable system to what we'd call a cross-line unit, which we call a line interface unit. And that controls the receiver lines of these WRUs. We have a backhaul network that gets the data back from the line interface units to the central recorder. And we have our own central recording system in the doghouse. So in terms of the equipment, it's really very straightforward. So the unit itself, it's got, if we start at the bottom left here, it's got dual hot swappable batteries. That gives a field cycle with a 12-hour production, 12 hours production per day of around about 20 days. We've got a GPS antenna there, which is used purely to locate the units on the line. We've got indicator lights that a sophisticated user can work out what's actually going on in the box. We have an antenna on the top, which is pretty rugged and it's spring-loaded, so it doesn't get broken. The case itself is stackable for easy transportation, and we have a standard KCK connector on the back here. So this is a single-channel unit. We also have a 3-channel unit that's available as well. In terms of our radio telemetry, we use a 2.4 gigahertz radio transmission band for our main transmission along the receiver lines. This is not Wi-Fi, it's our own proprietary network technology. And what we've done, we've really taken the protocol stack and made it so that the overhead is very, very small. So 90% of the bandwidth that's available is used to transmit data. This system really ensures that we have very, very good data integrity. And also, it's a frequency hopping modulation scheme that we use. So this means that the units can work without interfering with each other and without interference from external sources. Each of the radios is able to modulate its power output, so it will always try and work at the lowest power output that it can in order that the battery life is maintained. So you can see in this little animation, in the frequency hopping modulation scheme that we use, the peer WRUs are always working on a different frequency. And that ensures that we don't get in any data collisions. So these WRU units, or wireless remote units as we call them, they've got 2 functions. The first is that it acts as a 24-bit acquisition module, so basically inside there, you get an analog input, it's A to D converted and then buffered within the unit. Its second function is that it works as a radio relay, and those 2 functions are completely different, completely independent of each other. The timing discipline for the unit is actually synchronized over the radio network. So the GPS that's on the unit is switched off, and that makes a very big contribution to reducing our power budget on the unit. So any one of these units can be put on the ground and used as a radio repeater, which, for example, we can use this to what we call snake lines. So if you've got 2 adjacent receiver lines in a 3D survey, you can actually join them together and effectively have them working as a single receiver line from one line interface unit. And in terms of the data transmission, when one WRU is talking to the next one, it will, if there's a failure or if there's an error in the data packet, it will keep trying until it will repeat the send of the data until the packet is received in the central unit. But if one of these remote units actually falls over, or if it goes down for whatever reason, the line will automatically miss out that unit and go to the next one. And that means that the receiver line continues to transmit data without interruption. So that keeps our productivity very high. The line interface unit basically controls all of the wireless units in its receiver line. And its function is to convert the data from the wireless units basically into TCP/IP Ethernet packets at that point. So it then sends these TCP/IP data packets to the radio backhaul. And because it's TCP/IP at this point, it means that we've got a variety of backhaul options open to us. Our preference is to use a 5.8 gigahertz high-capacity backhaul, and that gives us about 100 megabits per second per 5.8 radio system. Alternatively, you can use a fiber optic cable, you can use UHF non-line of sight systems, and if you've got a cellular network in the region, you can actually use 3G or 4G to get the data back to the central. And of course, if you're onto a cellular network, the central unit doesn't have to be on the prospect. It could be at your head office. So typically, we would configure an RT system 2 on the ground pretty much like a cabled system for a 3D survey. And just here you can, oh, I just pressed the wrong button. Just here you can see how we've snaked the receiver line from this LIU here into this second receiver line. And then the line stops here where there's a no permit, so there's no access at that point. So that gives us very great flexibility in how the system can be used. In terms of the central, it's a Windows-based interface, but the servers themselves, they're Linux-based. And within the central unit, we have a size monitor that constantly gives you a view of the state of your spread. So, for example, in Kurdistan, where we were working over the summer, at one point the level of wind got up too high. It took us outside our noise specs. We were aware of that, so we were able to close the crew down until the wind dropped. So that was had a very good effect on the overall data quality. In terms of the central unit itself, it can interface to a multitude of energy sources, be it dynamite, vibrosize, weight drop, or indeed passive seismic nodes. And I know that Will Davies sitting down here has got another energy source that he's working on that he'd probably like to add to that list as well. So in terms of the command and control center, we have two modes based, sorry, I'll just go back there. We can see on the central unit, we have a 4-screen unit. You can see your data as it comes through. This is a microseismic frac job that we're working on, so this is just a continuous record. You can see here, this is using a sort of spoked wheel effect with a dozen or so lines, probably about 1,200 channels working in real time. And down here you have various charts that give status of all of the WRUs and the backhaul in the spread. So we've got two modes of collecting data from the WRUs. The first is continuous mode, which you typically use for vibrosize, also for microseismic monitoring. In this mode, there's zero overhead recording, so it has to be in real time. We can also do master-slave recording in this mode, and we use that a lot in microseismic monitoring. And indeed, we've got, we say continuous mode. We've done records that are a month long without any dropout of the system. A second mode is data on demand, where basically we record into the buffer in the wireless remote unit. And in this mode, it means that you can shoot salvos, for example, in 2D. If you're doing very long lines, where we know that the telemetry system is not going to be able to keep up with the rate the data is collected. So with this data on demand, we can then drain the telemetry if there's a pause in the acquisition that might happen in between dynamite salvos, or if the vibrosize units are moving up. We have a dynamic formation function within the unit as well, in that we need very, very little user intervention when we're deploying the units on the ground. Basically, we take the SPS or the SP1 file from the contractor, put that into our central unit, and then the wireless remote units use the GPS data to provide a location, and that then ties them into the receiver line. And all of that's done with very minimal intervention from the observer. We have an automatic skip peel function, which basically means that if a unit isn't transmitting, the central will try 2 times to get the data back from that wireless remote unit. If it's not able to do that, it will then jump to the next one. And the unit that's down will record the data for the remainder of that record, and thereafter it'll record a dead trace. But I guess you have to contrast that to what would happen in a cable system. If you've got a cut in the cable, you wouldn't be able to continue your acquisition until that cable was replaced. So that has very, very significant effects, beneficial effects on our productivity. Our data safe mode is basically a way of protecting data in the event of a line break. So as I said on the last slide, basically any disconnected WRU will continue to record data until the end of that record. And when it eventually is able to send the data back, that data is automatically integrated into the main data set. So the system will automatically skip heal itself so that we can continue the acquisition. But the important thing that should give the contractor and the oil company confidence is that there is no loss of data in the event of a line break. The other feature that we have is what we call rapid fire, which means that we can store data from hundreds of seismic records into one of these units. And because the data acquisition is decoupled from the actual data transmission, it means that we can continue to shoot more data instead of having to wait for all of the data to be sent back to the central unit. So the acquisition continues even as the telemetry system is oversubscribed. So basically what we have is a self-sustaining radio network that works in the event of a road crossing here where we've got a truck moving across. That might temporarily affect the data transmission, but as soon as the truck is out of the way, the data transmission just picks itself back up automatically. So in terms of the field applications, well, the system lends itself to high productivity vibroseis with a raft of different techniques that we can address, be it slip sweep, DS3, DS4, ISS, and indeed interleaved fleets are supported by the system. The system will work in master-slave mode, and we've had a number of occasions where we've worked alongside both cabled and nodal systems. And the system is now very scalable to large channel counts. So we can put in multiple backhauls to enable us to look in the future to be able to address the market for 100,000 channels and plus. So we know the architecture that we need to achieve that. Now look at a few projects that we've done recently. Hopefully, anyway, if the clicker will work. Yeah, so we'll look at some work that we did in Kurdistan, in an urban 2D and 3D in the United States, some radio range testing that we did for a service company, and the way that we do frac monitoring in the US, and also a case study in Indonesia. So this summer we were able to validate the fact that our system works on a large 3D, and this was the first time that we would really put a big system onto the ground on a commercial project. So the customer was Gazprom Neft, the Russian oil company, and the contractor was Asian Oilfield Services. And the project was in Kurdistan, and it was a 270 square kilometer survey. As you can see from this picture on the left, the terrain was pretty rugged. There were 3 minefields in the area, some of which had been cleared, some hadn't. So from an HSE perspective, it was pretty tricky. We took a completely cable-free system to run this. And it's fair to say that, and I'm sure the contractor would admit it as well, the crew was very inexperienced and their labour had no training whatsoever. So initially we had 8,000 channels on this job. There were 14 receiver lines in the active patch with 440 channels per line. And the live patch went up to 6,267 channels. The source was a single fleet of vibrosize recording at 2 milliseconds with 12-second sweep and a 6-second listen time. So one of the big issues that we had was that the local labour had no training whatsoever, and it was Ramadan when we started, and they really had no interest whatsoever in being there. So very, very often the labour simply wouldn't show up. We're challenged as well to make sure that in the very, very rough terrain that we gave guidance to our people as to where they could go, and that they had to stay within the demined areas. And that the upshot of that was that the travel times around the area were really much longer than they would otherwise have been. Didn't help that the fact that the temperature sometimes got up to 50 degrees C, which made it pretty uncomfortable when the air conditioning wasn't working. And our engineers were on site for the entire project. So after Ramadan, things really started to improve, and after the first week on the ground, our system was really pretty solid. And I think it's fair to say that there wasn't a single day when the system wasn't up and ready and waiting to go ahead of the vibrators. So productivity was never halted by the system. The project completed in 4 months, and on the basis of that, Gazprom awarded Asian an additional project, which is now being completed. They also put out a press release related to the RT System 2 about the world record of the highest number of cable-free channels that have been recorded in real time. And the good news for us as well is that this system's now been upgraded to 13,000 channels. So that's one of the field records for 4,700 channels. I don't expect you to count it, and that's the full 6,200 odd channels. That was all done live without the use of any cables, and that's the press release that Gazprom put out. So Gazprom also have they like the system so much that they've asked Geotech, the Russian contractor, to start testing our system in Russia, which we're currently gearing up to do at the moment. We also did an urban 2D in Indiana this year in an area that had a lot of culture, railway crossings, a lot of roads, a lot of external Wi-Fi hotspots, and none of that interfered with the system. We did some radio range tests with Halliburton and Pinnacle. They're looking to do some passive seismic. And this is a relatively small number of channels. They had a patch of 44 channels in thick vegetation and tall trees. So what they wanted to do was to test the radio performance in thick vegetation. They wanted to find out what the radio link quality was like and what the range was like. So we started off with a 120-meter group interval. And this is an example of the terrain, pretty heavily forested, a lot of bush, and fairly challenging, you would think, for a radio system. This shows how the grid was laid out on the ground. So basically, we established good links between all 44 stations at 120 meters in this forested area. We then disabled a station and allowed that to auto-skip heel, which gave us 240-meter interval between the radios. And the radios, they were still solid, and the seismic data was able to transmit at a high level. We then disabled 2 consecutive stations, which took us up to a 360-meter interval. And although the radio link was slightly reduced, it was still acceptable for data collection. So I guess the summary or the outcome was that we proved that the RT System 2's radio telemetry is capable of penetrating very severe, thick vegetation over hundreds of meters. And we still maintained the data to an acceptable level for the client. How much time have I got, Ian? Do you want me to stop?
Well, we do have a few minutes for questions, so
Right.
if you want to just terminate it.
Yep, I shall just
Gracefully.
whiz through this. This is basically we've done about 15 fracs with the system, typically around about 1,500 channels recording around the clock. And the interesting statistic is that there's a 90% reduction in data loss compared to a cable system with our systems. And overnight, for HSE reasons, the system's able to run without any people going out on the line to ensure its integrity. I have a fairly similar technique that's used by another company. Instead of having the wagon wheels, they have various patches located around the wellhead. This is in Indonesia in June. We did a 2D survey in Sumatra through some fairly thick jungle and plantation. And again, the system worked extremely well. The head count was much lower than anticipated, and the actual job was completed much faster than the contractor had anticipated. So this is my final slide. So to summarize, we know that the limitations of cable systems are well understood. We know that nodal systems can overcome some of the limitations of cable systems, but that they introduce more limitations that are not apparent in cable systems. Our system is a fully scalable real-time wireless seismic system with radio nodes that are efficient, reliable, robust, and self-sustaining. But there is still more work to be done, but we know what the path forwards is to be able to offer hundreds of thousands of channels in real time. So we're delivering today a 15,000 channel system, and by the end of this year, we'll be looking at 25,000 plus channels, and in 2015, we'll be moving towards 100,000 channels. So that's the end of my presentation. Thank you for listening, and sorry if I've overrun you.
So, any questions for John? Must be some. Yes, in front here.
Waterhouse. Thank you. Kurdistan is a very difficult area, you know, geographically because of mountains and difficult terrain. Would you say that your system is more commercially applicable in difficult terrain rather than kind of easier terrain, or would you say it's kind of 6 of one and half a dozen of the other? So it's not really terrain kind of determined in terms of its advantages?
I think it's probably the latter, actually. You've got advantages in all kinds of terrain, certainly where it's hostile terrain like that. If you've got minefields, for example, which are obviously an extremely significant HSE risk, if you can work around the mined areas without having to run cables, then that gives you a very significant advantage. The fact that it's real time in that area means that, especially when the weather actually can work against you because it was very prone to high wind, we knew when to close the system down. In easier areas, we've proved that you can drastically reduce the headcount on systems. So in Kansas, Dawson runs its most profitable crew using a 2,500 channel RT system 2, and they do that with 10 people.
Any others? Questions? So, yeah, we have one more.
Hello, thank you for the talk. Serge here. Could you please explain a bit more about the efficiency savings in terms of time over cable systems and if there's any savings per square kilometre surveyed?
Yeah, we've actually done some very significant work on this. And the main efficiency comes from the number of people that you actually need on the crew. And you know, we've seen that we can enjoy about a 30% reduction in the headcount across the board on our crews compared to cable and to nodal systems as well. Because you know, we'd thought going into it that our system would have a similar, that nodal systems would have, and our radio system would have similar reductions in headcount, but we found because of the infrastructure that you need in the base camp for the nodal systems, they don't actually reduce the headcount on crews. So I think really it's that the headcount is the headline, it's the headline saving.
There was a recent paper by E&I of Milan on that subject, which you may want to look up. It addresses that particular question. Any others? Okay, well, thanks again, John.
Okay, thank you.